The content in this presentation is covered on pages 191 through 195 of your textbook, and it's meant to help you achieve Learning Objective 31, which is to list the advantages and disadvantages of using a standard rain gauge versus weather radar to measure precipitation. Be sure to skim pages 191 through 195 before watching the video, and to read the chapter a little bit more carefully before attempting the online quizzes. The most common form of precipitation, rain, is probably the easiest to measure. Any open container that has a consistent cross-section throughout the can be a rain gauge. And in general practice, more sophisticated devices are used to measure small amounts of rainfall more accurately and to reduce loss from evaporation. The standard rain gauge has a diameter of about 20 centimeters or 8 inches at the top. Once the water is caught, a funnel conducts the rain through a narrow opening into a cylindrical measuring tube that has a cross-sectional area only 1/10 as large as the receiver. Consequently, rainfall depth is magnified 10 times, which helps you read the measurements more accurately to the nearest centimeter or hundredth or centimeter. It's 2.5 1/100ths of a centimeter, about 1/100th of an inch. When the amount of rain is less than that, it's generally reported just as being a trace of precipitation. So in the database, you'll see a TR instead of a number. Remember that there's nothing automated about a standard rain gauge. And that means that some poor researcher's graduate student is going to have to spend a year or two running out to this gauge every hour on the hour to open the device, read and record the depth of precipitation, dump out the gauge and reset it. And the end results will be a table that looks something like the one that's shown here, with a column for date and time, another for the depth of water in the gauge, and a third for the cumulative depth of precipitation. And notice that we're talking about the total precipitation for a given day. So about half of the rain from this event falls on the 1st of February and half of the rain falls on the 2nd. Even though in terms of time, it was raining for twice as long on the first day as it was on the 2nd. That means the real cumulative depth for the entire storm was more like 2/10 of an inch. But for that day, it'll only be reported as 1/10. So if your goal is to compare precipitation on the 32nd day of the year, this works out well. But if you're hoping to use the rainfall data to relate to other surface phenomena like river flow downstream, it's probably better to treat this as a single event and see how long it takes for the local streams to respond to that input of water. In addition to the standard rain gauge, there are several types of recording gauges that are routinely used. These are not only record the amount of rain, but they also time the occurrence and the intensity. So you can end up with an amount per unit time. So many inches per hour or inches per day. Two of the most common of this type of gauge are the tipping bucket gauge and the weighing gauge. The tipping bucket gauge consists of two compartments. Each one is capable of holding a 1/100th of an inch of rain. So that's this silver thing that looks like a teeter-totter. It is situated at the base of the funnel, right? Here's the diagram and on the left, and here's the picture. When one of the buckets fills, in other words, it has exactly a 1/100th of an inch of rain in it, it'll tip and empty the water. And meanwhile, the other bucket takes its place at the mouth of the funnel. Each time a compartment tips, an electrical circuit is closed, and 1/100th of an inch of precipitation is automatically recorded on a data logger. And the output from a tipping bucket gauge then is really just a list of the points in time when the circuit closed. So you can imagine that makes a very different kind of precipitation graph. A weighing gauge collects precipitation in a cylinder that rests on a spring balance. And as the cylinder fills, the movement is transmitted to a pen that records the data. So all rain gauges are susceptible to inaccuracies, and the tipping bucket rain gauge is known to underestimate heavy rainfall by 25% because of the rainwater that's not collected during the tipping movement of the bucket. Also, wind can lead to measurement errors by either causing too much or too little precipitation to enter the collecting container. In addition, because rain gauges provide data for specific location, the significant variations in the amount of precipitation that reaches the ground over a whole region can't be estimated accurately. When snow records are kept, two measurements are usually used: the depth of the snow and the water equivalent. One way to measure the depth of snow is using a calibrated stick, like a yardstick. And the actual measurement isn't difficult, but choosing a representative spot really can be. Even when winds are light or moderate, the snow is drifting freely, and as a rule, it's best to take several measurements in an open place away from trees and obstructions, and then average them. So to obtain the water equivalent, samples have to be melted and then weighed or measured as rain. The quantity of water in a given volume of snow is not constant. So you may have heard media weathercasters say every 10 inches of snow equals 1 inch of rain, but the actual water content of snow may deviate widely from that figure. It may take as much as 30 inches of light and fluffy dry snow, 30 to 1, or as little as 4 inches of wet snow, 4 to 1, to make an inch of water. So to measure the mountain snowpack, which produces 75% of the water supply for the western United States, automated weather stations employ snow pillows that have been installed at more than 600 sites. A snow pillow consists of 2, 3, or 4 large panels that measure the pressure exerted by the weight of snow that collects on them. Because snow pillows have large surface areas and measure the water equivalent of snow, they provide a good estimate of the volume of precipitation, which is really what we are after. Using weather radar, the National Weather Service produces maps like the one in figure 5.27, in which the colors illustrate precipitation intensity. I'm showing you a similar map, not the same map, but this one is for the Pacific Northwest. As weather radar has been developed, it's given us an important tool to track storm systems and the precipitation patterns that they produce. So even when the storms are as far away as a few hundred kilometers, radar units have transmitters that send out short pulses of radio waves. The specific wavelengths selected depend on the objects being detected. When radar is used to monitor precipitation, wavelengths between 3 and 10 centimeters are employed. Radio waves at these wavelengths are able to penetrate clouds composed of small droplets, but are reflected by larger raindrops, ice crystals, and hailstones. So the reflected signal, which is called an echo, is received and displayed on a TV monitor. Because the echo is brighter when the precipitation is more intense, modern weather radar is able to depict both the regional extent and rate of precipitation. Also, because the measurements are in real time, they're particularly useful in short-term forecasting. Despite its usefulness, weather radar doesn't always show what's occurring at ground level, though. For example, radar may detect precipitation high in the atmosphere that doesn't reach the ground, like virga. Also, weather radar detects ground clutter, like trees and buildings, and that complicates the image that's received. So occasionally, radar receives echoes produced by dense swarms of insects or birds. In addition, conventional radar systems can't distinguish rain, liquid water, from solid forms of precipitation. Fortunately, the National Weather Service is upgrading most of its local forecast centers to a new kind of radar called dual polarization radar. And that produces two-dimensional images. And those images will help forecasters distinguish between rain, hail, snow, or sleet from other flying objects, including tornado debris. We're going to see a lot more of the Doppler radar when we look at tornadoes. Use the content provided on the Canvas site as well as any outside internet sources to verify that you can formulate answers to these questions. If you can comfortably answer them, you are in great shape. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.